We continue with our discussion on the TCP and UDP protocols in this lecture as well. Here in the second part of this lecture, we shall be looking at the actual header fields of both the TCP and UDP protocols, and in particular we shall be looking at the process of TCP connection establishment and also connection termination, because these are a few very interesting things which can lend itself to some kind of network based attacks that we shall be talking about. Okay. So, let us start with TCP. TCP, we have already mentioned that at the transport layer level we have a host to host connection facility. So, TCP supports host to host communication facility and it supports a set of features. The features are like this: two processes can communicate among themselves, a process on a local machine and a process on a remote machine. There can be a process here, there can be a process here, they can communicate. Stream delivery service, the data that are being transmitted, these are called segments, they are considered to be as a stream of bytes. A stream of bytes are sent, a stream of bytes are received at the other end. This is said to be a stream oriented service. Full duplex means both way communication, two way communication. Multiplexing and demultiplexing means multiple active connections may be present between the two ends and multiple packets for multiple connections can flow through the same links and same logical links. These are called multiplexing and demultiplexing. And TCP ensures connection oriented and reliable service. This briefly we have mentioned earlier, that there are a few features using error control, retransmission. So, it tries to ensure this kind of features. Now, you look at the whole TCP/IP protocol family and you can see that TCP sits here, TCP is here. Below TCP there are several protocols at the network layer level where IP is the dominant protocol, and there are a few sister protocols which are there which have very specific purposes. So, the point to note I am just repeating. So, although TCP provides a connection oriented reliable service to the applications at the higher layer, but all data transmission has to take place via IP, and IP is a unreliable datagram service. So, TCP has to do a lot of bookkeeping, management, buffering, so that all this error correction and streaming and these reliable facilities can be provided to the application. Now, let us look at these diagrams. This first diagram actually shows you the conceptual view of TCP. This is a sending process, this is a receiving process on two different computers. This is the TCP layer on this and this is the TCP layer on this. So, TCP provides a host to host logical connection. This is not a physical connection, a conceptual connection. So, you have this pipe that is being shown here, this represents the logical connection, and over this logical connection a stream of bytes are flowing. This is how a TCP communication system looks like. Now, let us look into some more detail inside TCP, which is shown in the next diagram. You see both the sender and the receiver they maintain some kind of a buffer. Buffer at the sender side will contain the message that it is trying to send. It is a stream of bytes. The receiver also will maintain the buffer, whatever comes it will put in the buffer, and both the sides are keeping track of how many bytes have been sent, how many bytes have been received, and so on and so forth. Like you see in the sender process, there are some bytes marked in pink which indicates the bytes which have been sent, already sent. The bytes marked in gray indicates which have not yet been sent, and the process, when it is generating some data to be sent, it will be storing them into the buffer from the next available location onwards. In this way, the buffer at the sending side will get filled up, and on the receiving side similarly, some data is being received. This pink one says that this data have been received, but not yet read by the receiving process, and whatever comes over the network, they will get stored out here starting from the next available location onwards, and the receiving process will be reading the bytes one by one from this pink part, right. Now, TCP maintains this buffer automatically. You see, due to some error in between, it may see that somewhere in between there is a vacancy, all bytes have not yet been received. So, there will be an acknowledgement mechanism, the receiver will be requesting the sender to send back the missing bytes again, so that the receiving process can be forwarded the bytes in the correct order. Okay. And the other point you notice that, which is just depicted in this diagram, a similar diagram, it shows some basic data transfer unit called segments. You see, at the network layer level, we talk about packets, packets are being transferred. At the data link layer level, we talk about frames, frames are being transferred. But at the transport layer level, at the TCP level, we talk about segments, data segments which are nothing but stream of bytes, multiple segments are being transmitted one after the other. Okay. This is the concept. Now, let us look at the header format of the TCP protocol. Just like IP, I am showing this bit numbers on top starting from 0 up to 31, which indicates that each row of this indicates a 32 bit quantity, 4 bytes. So, first you have source port number, destination port number, 16 bits each. Then we have a sequence number. Well, sequence number means, I told you that data are being sent in units of bytes, stream of bytes. Sequence number is like a byte number, which byte number is being sent. This is a 32 bit quantity. So, which means maximum segment size can be 2 to the power 32, quite large. Similarly, acknowledgement number is also 32 bits. Acknowledgement number is coming from the other side. It tells, the receiver tells the sender that, well, I have received up to byte number so and so, that is the acknowledgement number. So, that the sender will know that, well, up to this byte number has already been received. So, I need not keep it in my buffer anymore, let me remove it from my own buffer. Okay. Then there are some other fields, like there is a header length, just like TCP, there is some reserved field, there are some flags which I will talk about. There is a window. Well, window is like that buffer I told you, na? Some data are being sent, some data are being received. So, there is some windows that are maintained by both sender and receiver. This is called a sliding window protocol. but I am not going into detail of this. So, this window specifies this so called sliding window and is used for flow control. Flow control means the maximum speed of data transmission you can control by changing the size of this window. Okay. And of course, there is a checksum for correcting errors, detecting errors, and there is an urgent pointer. Sometimes as part of the TCP packet you can send some urgent message, and urgent pointer actually points to some part of the data where that urgent message is located, okay? And some option field is also there. So, the TCP header is typically minimum 20 bytes and can go up to 60 bytes. So, a brief explanation. Source port already I have mentioned, destination port. This identifies the process at the local end and at the remote end. Sequence number, I am just repeating, this is used for keeping track of the bytes being transmitted for the purpose of reliability. Each byte is assigned a 32-bit number, and as the bytes are being transmitted, that number is incremented by 111 like that. Okay. Fine. Similarly, from the other side, acknowledgement number is coming. The remote host will acknowledge receipt of the data. It will contain the number of the next byte expected. Like say, suppose the receiver has correctly received up to byte number 1000, let us say. So, it will be sending back an acknowledgement saying acknowledgement 1001. So, it will be sending back an acknowledgement packet with the acknowledgement number field as 1001. Okay. Now, header length is a 4-bit field. It is just similar to the IP, and the IP header also has a header length field. It specifies the header length in multiple of 32-bit words. Okay. So, minimum value is 5 because minimum header size can be 32, can be 20 bytes. So, it can be 5 minimum. Well, these are interesting. There are several flags in the flag field in TCP. There are in fact 6 flags: urgent, SYN, ACK, FIN for finish, reset and push. They are used in combination for various reasons. The 6 of the most important reasons are mentioned here. Well, if there is any urgent data that is carried by the TCP packet, urgent data may be some kind of interrupt processing, some important thing need to be handled. So, then the urgent flag will be set to 1, and I mentioned the urgent pointer, there is an urgent pointer field, it will be pointing to some place in the data part, that urgent data will be stored there. So, if the URG pointer is set to 1, it means that the urgent pointer is now active. In TCP, whenever you are doing a connection establishment, you are requesting for a connection, then you set this SYN flag to 1 and ACK flag to 0. This combination means connection request. Similarly, connection confirmation, I will show the details later. So, when a connection is confirmed, then the SYN and ACK both are set to 1, right. And during sending, if the sender has no more data, it has finished sending the data, then the finish flag will be set to 1, so that the connection can be released. So, when the connection has to be terminated, this FIN flag is set to 1. And sometimes you may need to reset a connection due to some problem, then RST bit is used for this purpose. Some connection attempt you do not want to accept that connection, then also you can send the RST bit, the connection will be rejected. And there is the last bit push bit, this indicates a push function. This can also be used to indicate end of message. So, when a message is finished, you can set the push flag to 1, it will tell the receiver that there is no more bits in the message. Okay. So, these are the flags and the ways they can be used. Window is a 16-bit field. Now, this field actually tells you how many bytes you can send beyond the bytes acknowledged. Like, let me give an example. This is the sender, this is the receiver. Sender is sending bytes one by one. Suppose the receiver has sent back an acknowledgement. It has said that, well, I have received all bytes up to 1000, next byte I am expecting is 1001. Okay. Now, for the sender, let us say the window field is 100. Let us take an example. This means that the sender can now start sending byte numbers starting from 1001 up to 1100 without waiting for an acknowledgement. This window size actually tells how many bytes the sender can send without getting the acknowledgement. Once the window is full, finished, all 100 bytes have been sent, then the sender will be waiting and idle. It will be now waiting for the acknowledgement to come back. So, as you can see, if the window size is larger, you can send more data and wait less, and then wait for the acknowledgement to come. But if the link is slow, then possibly window size will be made smaller. So, by adjusting the size of the window, the rate of transmission of data can be controlled. So, you can use something called flow control using this window, and the window size is referred to as window advertisement. As I mentioned, it can be increased or decreased. And finally, there is a checksum. Checksum is used for error correction, and this checksum is applied not only for the header, but for the entire data segment. Like in the TCP protocol, you have the header, you have the data, and there is also something called a pseudo header. This checksum is applied to the entire part of it. What does this pseudo header contains? Pseudo header borrows some of the fields from the underlying IP. That is not strictly part of the TCP header, but it borrows something from IP like source IP address, destination IP address, which protocol it is using, TCP or UDP, and what is the length size, right. Because this information are also important, so that TCP can verify that whether the packet that has come, the message that has come is actually coming to the right IP address or not. So, just for an additional level of checking, this pseudo header is maintained. And for computing checksum, that same ones complement, just add up and then take ones complement of the result. Same algorithm as is used for IP checksum is used here also. Now, let us look very quickly at TCP connection establishment process. This is interesting. You see, here there is a client, and client is trying to establish a TCP connection with a server. There is something called a three-way handshake protocol which is followed here. The first step is to initiate the connection. What it does? The client will send a packet with the SYN flag set. First, the SYN flag is set to 1 and a packet is sent. Well, here some sequence number will be carried with the packet, let us say 100 as an example. So, when the server receives this initiate connection request, the connection is still not complete, this is incomplete connection. Server responds by sending a SYN ACK packet. So, this is going in this direction. SYN ACK means SYN is also 1, ACK is also 1, both these flags are 1. This will be going in this direction. And here sequence number will be from the server to client side, let us say this is 200 and this sec was 100. So, now this acknowledgement number will be 101, next one. So, after receiving this, the client will now know that, well, yes, now the connection can be established, and what is done finally is the client sends back the last packet, it is an ACK packet. So, the final acknowledgement ACK equal to 1. Here this sequence number was 200 was received. So, now ACK will be 201 and previous packet was carrying sequence number 100. Now, this will be sequence number next one 101, let us say. So, when server receives this, connection is finally established. So, the idea is that when the server receives the first packet, it gets ready for the connection, that, well, there is a connection request, let me keep aside some buffer, some entry in the table, so that this connection can be taken care of once my 3-way handshaking is done. So, server sends back and client finally sends back again, then only after this 3-way handshake the connection is said to have been established. Okay? This is how TCP connection is established. But look at a scenario like this, which we refer to as half open or incomplete connection. Well, that same diagram I am showing, the client is sending a request, server gets that request. So, it gets ready for the connection, it sends back a SYN ACK. But what the client does, well, either deliberately or otherwise accidentally, it does not complete the connection, means it either does not send back the final acknowledgement or it had sent, but due to some problem it did not reach the server. So, what will happen? The server is waiting indefinitely for the connection to be completed. This is something which we refer to as half open connection, right. So, now server is in a state where it was expecting the connection request to be completed, but it is waiting. Well, of course, there can be a timeout mechanism, that means it can wait for some maximum amount of time, then it can assume that due to some error this connection is not going through. Let me discard this. But the problem is, this feature of TCP actually has led people to mount some kinds of attacks on systems. So, this is a simple attack scenario I am just mentioning. Suppose some hackers decide that I have to target that particular computer. So, many of these hackers, they come together and they try to send a large number of TCP requests to that particular server, some particular computer. And for each of the requests, what they do not complete the final ACK, they do not send the last ACK. So, the server will be receiving a large number of requests, but none of those requests will be completed. So, the size of the table will slowly get filled up, that means connection request has come, not yet fulfilled. So, finally, the table will be full, there will be a finite size of the table. So, all future connections will be denied, because there is no space to keep records in the table. So, even the legitimate connections will get denied. This is something which is called denial of service attack. So, this was one of the simpler ways to mount denial of service attacks based on the TCP protocol, right. Okay. And lastly, talking about the TCP connection termination, well, I am just illustrating it here. This is the client, this is the server. Well, I am showing it in the context of an ongoing communication. Suppose the client was transmitting some data, right, some data was coming and was coming to the server. So, server was doing some read and read was successful. It was returning some number greater than 0 means read was successful. Now, when the client wants to shut down the connection, terminate the connection, it will send a packet with the FIN flag set to 1. What the server will do, means it will send back an acknowledgement of both the data that it has received and also this FIN it has received, right. Then in response to this data it has received, maybe the server is doing some final write, some data it writes back to the server and server finally reads. And then the server is also done with the connection, server also wishes to close. So, it sends back another FIN to the client and client finally acknowledges data and FIN and now the connection actually closes. So, it is like a 4-way handshake, 4 packets are going, one in this direction, second in this direction, third in this direction, fourth in this direction. So, this is some kind of a 4-way handshaking that is going on for TCP connection termination. This is how it works. Now, lastly, for the UDP packets, the header format is very simple. You see, the IP layer provides a datagram service. This UDP is also datagram, but it contains a few other fields, like because it is at the transport layer level, it contains the port numbers, it contains a checksum, it also keeps track of the total message length. These are the additional things that are there in the UDP. And here the total header size is 8 bytes, 4 plus 4. You see, for UDP, because the header size is small, the overhead is less. So, for many applications where reliability is not that important, you need fast data transmission, no connection establishment required. You see, for TCP you need 3-way handshaking for connection establishment. For UDP there is no question of connection establishment, you just send the data packet, it will be routed and go. UDP is faster in that sense. So, there are many applications where you prefer speed to reliability. So, these are the 4 UDP header fields I already mentioned, right. So, with this we come to the end of this discussion on TCP and UDP. In the next lecture, we shall be talking about something like IP subnets, how subnets can be created within IP networks and what are the advantages therein. Thank you.